All right, good morning, ladies. So let's see here. So first things first, sorry I don't have your exam graded yet. So that's the first thing I'll talk about. I was supposed to do it over the weekend, but it turned out this was actually a religious holiday for us this weekend. So we ended up bringing the kids all over the place. So we spent the day in Bowling Green on Saturday and then brought them to Holiday World yesterday. So unfortunately I didn't grade that, but I'll have it graded soon. Hopefully, if my children give me time to do it. So anyways, yeah, and if you just came in, we're just talking to Tara. So yeah, so unfortunately, if you got 0 points for the pre-lab, don't worry, I'll go through and give everybody their points back. It just depended on how you answered the question. So I wanted it exactly perfectly. So I'll go through and look at what your answers were and give you all points back for that. So don't worry too much about that. So don't freak out that you got 0 out of 30 points. Okay. And let's see, other announcements. So this morning I posted exam 4 examples. So that has been posted. Don't forget our next exam is going to be Friday. So this Friday. And I also posted the extra credits for that. So all that stuff is now up on Blackboard. So you have access to all those beautiful things. So good. So we had been working in chapter 20. And the last thing that we looked at were these velocity selectors. So let's quickly kind of talk about velocity selectors again. So again, velocity selector is when I have parallel plate capacitors, which are to create an electric field. So here's my parallel plate capacitor. So inside of here, we create an electric field. So here's an electric field. And then we're going to cross that with a magnetic field. So perpendicular to that will be our magnetic field. So here's my magnetic field, perpendicular to this guy in all locations. So that if I took a charged particle, let's say this is charged particle, it was horrible. Call that Q. There we go. So that if this guy goes through the plates, if his velocity is just correct, then he's going to go directly through these plates with 0 net force acting on him. So he's not going to be deflected upward or downward, depending on exactly this velocity. So it turns out for this to happen, the velocity then must be equal to the ratio of the electric field to the magnetic field. So again, if the velocity here is greater than that, what's going to happen in this case, then he's going to deflect upward if it's a positive charge, because in this case, the magnetic force will be greater than the electric force, so it's going to deflect upward. If the velocity is less than this, then he's going to deflect downward, because in that case, again, a positive charge will feel a force electric downward, which will cause it to be deflected downward since the electric force would be greater than the magnetic force. So these were the velocity selectors. And yeah, we talked about some examples of this. These are used in mass specs. These were used in the development or the discovery of the electron. They're used in a lot of different places. They're also used in particle colliders. So places like CERN and Fermilab, which is in Chicago, and other places, these things are used all the time. So the reason I'm talking about that is because we're going to start off with a group assignment, which has to do with velocity selectors. So this is also up on Blackboard, put this up this morning. So this says that we have an ion source, produces lithium-6 ions, which have a charge of positive E and a mass which is 6 times that of the proton. So it says the ions are accelerated by potential difference of 10 kilovolts and pass horizontally into a region in which there is a uniform magnetic field of 1.2 Teslas. So it wants to know what is the size of the electric field that will allow these guys to move through this region completely undeflected. Okay, so this is what we want to know. So let's kind of draw the scenario here. So basically, we have some region here, 10 kilovolts worth of potential. So we're going to take our lithium ions. So this is our lithium-6. And we're going to cause this guy to go from 0 initial velocity, so he accelerates through and then comes out of the region with some final velocity. Then we're going to take the parallel plate capacitor velocity selectors here. So that again, this is a positively charged, this is negatively charged to create the electric field. And we're going to cross that again by the magnetic field. So our magnetic field will point in this direction. And we're told that the magnetic field has 1.2 Teslas worth of field. And what we want is for this thing to go through this region, again, undeflected. So we want to know the velocity then must be equal to the ratio of the electric field to the magnetic field. So basically, you want to now use this information to determine what is the electric field. So what's the value of the electric field? So here, you have to use way back what we used in chapter 2. So to do this part, you have to use conservation of energy. So the change in kinetic energy plus the change in potential energy is equal to 0, since there's no work done by a non-conservative force. So here, the initial kinetic energy is 0. The final is non-zero, so it's going to be 1/2 mv squared. There we go. Plus the charge, which we're told is E, times then the change of potential. The change of potential in this case we know is 10 kilovolts, is then equal to 0. So from here, you'll find that velocity. From that velocity, you know the magnetic field, so they can solve for the electric field. So the electric field then is just going to be the velocity times the magnetic field. So that's it. So not too bad. So I'll give you, I don't know, 10 minutes or so to kind of work on that in your groups here. And then we'll start talking about some new stuff. So how many people we got today? 2, 4, 6, 8, 9. Okay, so we can do 3 rooms today, I think. Yeah, all right, here we go. Hello, ladies. How we doing?
Okay. What is the mass of the proton?
Oh, 1.67 times 10 to the minus 27 kilograms. So your lithium atom is then 6 times that. Cool. I'll be right back. Hello there.
Hi.
Bang.
Okay, we are aware that this is easy, but what the mass of lithium is?
So it's 6 times that of the proton. So the proton's mass is 1.67 times 10 to the minus 27 kilograms.
So that times 6?
Times 6, correct.
Oh, okay. That's what it was saying then when it says, because it just says a charge of plus E and a 6 times that of the proton.
Oh.
So it doesn't have the word mass in there.
I apologize. Let me put that in here.
Okay.
I can't always be perfect. There you go. So now it says that. I'll upload that later. Okay. But yes, so it's a mass of 6 times. Good.
I'm at work.
How are we doing, ladies?
Good.
I'm working with the calculator for the velocity right now.
Nice.
All right, let's see.
Our most hated calculators. Good.
I got really lucky that I was far enough through the last exam before it happened, but I pressed a button and I didn't know like which one I did. Like it did something strange to the notation on my calculator. And I was like, no, I don't know how to fix it. I've fixed it since then, thank goodness. But
There you go. Good.
I was like, I don't think I have time to fix it during the test. So I was nervous.
I could imagine. Yes.
I got 1.38 times 10 to the 6 meters per second. What'd you guys get? The velocity.
That would be to the 6th. Same.
Yes, love that.
Yeah, that's what I got as well.
Cool. Look at us.
Very nice.
We can be wrong together if it's wrong.
That's true. 3 people wrong simultaneously was a little suspect, but
Right.
We're all confused in exactly the same way.
exactly. All right, I'll be back. Let me go check on the others.
Okay.
All right, I'm back again. How we doing?
For the electric field, I got 6.79 times 10 to the 5th.
Okay, sounds reasonable. I think that's okay. Here, let me calculate it real quick. Yeah. Yeah, typically the electric field is huge compared to the magnetic field. So typically, so. There we go. 2, 6, 10 to the minus 19. The mass, was equal to 6 times 1.67 times 10 to the minus 27. Magnetic field was 1.2. V was 10 kilovolts, right?
Mm-hmm.
And that's it, right? Yeah. Okay, good. So we should have that E is equal to V, which is the square root of 2 times V divided by the mass. And all times B. Yeah, so I got 1.69. No, that looks too big. Times 10 to the 15th. No, that's not right. Oh, sorry. I forgot my E. Multiplied by the charge. There we go. So 6.78 times 10 to the 5th. Yeah. Good. Very nice. All right. Good job. How we doing?
We got the velocity, but it's really high. Is that right?
Yeah, it should be something to the 5th or to the 6th, maybe to the 6th.
I got to the 5th, yeah.
To the 5th, okay. Yeah, so if I calculate the velocity alone, do that. I got, 5.65 times 10 to the 5th. Yeah.
That's what I got.
Yeah, they move pretty quick.
I was like, dang, that's pretty high.
Yeah.
And then you just multiply that by 1.2.
That's it.
Cool. I love that. That's the whole test. So 6.78 times 10 to the 5th.
Yep. Volts per meter or newtons per coulomb. Correct. Very good. Good job. I'm gonna check on these guys.
Because you just multiply that with the magnetic, right? Or the velocity with the magnetic.
Mm.
Yes.
Yep.
That is correct.
And I'm blanking. What is our unit for electric field?
It's either newtons per coulomb or volts per meter.
Okay. Probably then volts per meter in this case.
Either one is fine. They're both the same thing. So
Volts per meter.
very good. So 6.78 times 10 to the 5th. Is that about what we got?
Nope. What happened there?
Well, that's for the electric field. What'd you get for the velocity?
I got 1.38 times 10 to the 6th meters per second.
For the velocity?
Mm-hmm.
Did you multiply the mass times 6?
Nope.
No.
Okay. Okay. So that's where we're wrong. Okay. Because remember, the mass of the lithium is 6 times that of the proton. So
Okay. I guess I was very
you read
confused.
that to be 6 times the charge. And then when you had written it in class, like for the whole class as it is, like just to get us started, you wrote just E. So we were like, maybe that's a typo. And we just left it out.
no, the mass is 6 times that of the proton. Sorry.
Okay.
Okay.
Yeah, I updated the wording, so let me rechange it on there. So
So the mass is just times 6.
correct. So yeah.
Let's redo this.
Mhm.
I'm sorry, I'm not perfect all the time.
So disappointed.
I think I'd be more disappointed if I was perfect all the time. So
That would be scary, meeting a perfect person.
that's true. That's very true.
10 to the, what is it? Yeah.
All right. So I have uploaded the new version. So
Oh, the calculator is not doing what I want. Okay.
Okay.
There we go. That's better.
What did you say the answer should be?
or which one?
The electric field.
6.78 times 10 to the 5th.
Cool. We're good now.
Nice. Okay.
Yep.
Good. All right. So I will then disband everybody.
Okay.
All right. All right, welcome back, everyone. Oh, good, that went well. So next thing we're going to talk about is what happens if I take a loop of wire, which is carrying a current, and I place that into an external magnetic field. So let's say here I have a rectangular loop of wire. So the top and bottom portions here are length B, and then the side portions here are both going to be A. I'm going to put this into an external magnetic field. So this is a front view of it. So basically the magnetic field is kind of penetrating, going into the board or into the page here. If I look at it at a side view, what's really happening is that this loop of wire is actually tilted at an angle, and then it has the current running through it. So in this case, I'm taking the current is running in a counterclockwise direction, which means if I'm looking at it from the side view, so I'm looking at it from this side over here. So I'm looking at it, here's my eye looking at it from over here. So I'm seeing the current on this portion here. So I'm looking at this leg here. So here, if the current's going around in this direction, that means the current's running up through it here, which is why it's running in that direction. And magnetic field here is in the horizontal direction. So basically, what we can see is what we know is, going back to our force on a loop of wire, or at least on a straight wire, we know the force on the wire is given by the current times the length crossed by the external magnetic field, or that's the same thing as I times L times the magnetic field times sine of the angle between the two, if I'm looking at simply the magnitude. So basically what that tells us then is what? Let's look at all the different forces. So here, first of all, this is going to have a force. So again, right-hand rule says we point our fingers in the direction of the current, so it's in that direction. We would then rotate our palm, curl our fingers towards the magnetic field, which is going inward, which means our thumb would point down. So on the top portion of the wire here, we're going to have a force which is pointing downward. Right? So here, I'm going to have a magnetic force which is pointing downward. On this portion over here, the current is now going down, so I put my fingers downward. I curl towards the magnetic field. My thumb would then be pointing into the center of the loop. So on this portion, I'm going to have a force in this direction. Bottom portion here, my current is now going in that direction. We curl towards the magnetic field, so our thumb would be pointing upward. So here we would now have force FB upward. And on this portion over here, again, current is now going up, curl towards the magnetic field. So in this case, our thumb would be pointing towards the center of the loop. So this would now be all the forces. So in each part of these different parts of the loop, they all have forces, but each one of those forces are going to cancel each other. And the reason for that is because if we look at this portion here, the force on this guy is then going to be the current, I, which is the same current, times the length, which is going to be A, times D. The force over here on this portion, it's going to be F is equal to also I times A times B, but those two forces are equal and opposite, which means they're going to cancel. So these portions of the force will cancel each other. Up here and down here, the force is then going to be F is equal to I times B, which means this force is also equal and opposite to this force. So these two are also going to cancel each other. So what that means then is that the net force acting on this loop of wire is simply equal to 0. So the sum of the forces is equal to 0 since all of these are equal and opposite to each other. These two are equal and opposite, these two are equal and opposites. So all those forces are going to cancel, which means that there is no net force. So no net force just basically means this thing is not going to accelerate. However, what is going to happen though is that what? So let's look at the side view here. According to the side view, we now have what? This portion of the force is acting down this way. Okay? So this one is pointing straight down. So I have this FB. This portion is pointing up, so I have this FB. So what is going to happen is, even though there is going to be no net force, what will happen is, if this is my loop, right, which is sitting at this portion is going to pull down, this portion is going to pull up, which means it's going to do that. Right? So this thing is going to feel a torque, because it's going to rotate. So even though this one is being pulled down, this one's being pulled up so that it's not accelerating, but it is going to rotate to try to align itself with the magnetic field, which means it is going to feel a torque. So this thing will feel a net torque. So let's look at the net torque. So let's look at the sum of the torques. So remember that torque magnitude is equal to the distance. So this is the R vector times then the force times sine of the angle between the two. So here, what's going to happen is what? Our r vector, since this thing is going to rotate about the central axis, r is going to start here at the center, point here. So this is going to be our r vector. So r in this case is going to be exactly 1/2 of a. So here, this is going to be the torque on the top. So let's write this as torque top, plus then the torque on the bottom. So it's going to be the same thing as the distance, which is a over 2, times the force, which is the magnetic force, which we already did up here, but we'll skip that portion for now. Times sine of the angle. So in this case, the sine of the angle is, if I extend this guy in this direction, right, the angle then is going to be this angle, which is the angle between the two of those. So this is my angle theta. Plus a divided by 2, because this distance across here is the same, times FB, times also sine of that angle. Right? Because here, again, if I extend this in this direction, that's this angle here, which is theta. Pardon me. Okay. Now, these two torques are in the same direction because this one's pulling and it wants to rotate this portion in this direction. This one's pulling and also wants to rotate in this direction. So those two torques are in the same direction. So that's why there's this positive sign here. Now this force is the same as this force. This angle is the same as this angle. Everything is the same. So this is simply the same thing as A times FB times sine of the angle between the two. FB in this case corresponds to this FB, which is the same thing as I times B times B. So I'm going to finally write this then as what? I times A times B times magnetic field times then sine of the angle. This quantity here, this quantity here is something which we call the magnetic dipole moment. So we're going to write this then as mu, where mu is what's known as the magnetic moment, which we're going to write as I times AB. But A times B is simply the area of this loop. So this is the same thing then as I times A, where A then is equal to the area of the loop. Now, if we compare that to what we did before, we can actually see that this thing is actually a cross product, which means in general, we're going to rewrite this then as mu, which is written as a vector, crossed then by the external magnetic field, or magnitude-wise, this is going to be mu times B times sine of the angle between the two. So this is going to be the torque then on the dipole. Now, question is, what direction does mu point? And that's a question of what direction A points, which brings us to our next right-hand rule, which is known as right-hand rule number 3. So right-hand rule number 3. So right-hand rule number 3 says that what? Step number 1, curl fingers in direction of the current. Step number 2, thumb, which again is perpendicular to the hand, points in direction of the current / the area. Okay. So let's use that here. So here, what that said was that what? Let's draw a rectangular loop again. So here's my rectangular loop. This was A and this was B. And we had current running through it in this direction. Okay. So the right-hand rule number 3 says is that we're going to curl our fingers in the direction of the current, which means our thumb then is going to be pointing towards me, which is in the direction of the magnetic moment of the area. Okay. So this tells us then that the direction of the magnetic moment is pointing towards us. Okay. So again, curl our fingers in the direction of the current. Our thumb then points in the direction of the magnetic moment. In this case, the magnetic moment will be pointing towards us. Okay. Or if I go back to the previous page, what that means then is, what color have I not used? We'll use blue. So in this case, we'd curl our fingers in the direction of the current. So that's going around in this direction. So in that case, our thumb would be pointing down in this direction. So this is the direction of the magnetic moment. So that means this angle here, so if I extend the magnetic field, so let's draw the magnetic field through the center, close, then this angle here is the angle theta, which is the same as this angle here. Okay. So all that's happening here, let me kind of redraw it on the side. B points in this direction. The magnetic moment then is pointing down in this direction, which means that this angle here is that angle of theta, which is the angle between the magnetic field and the magnetic moments. So that's this angle here, which is the same as this angle here. So this is the torque then on a magnetic dipole moment. So basically a loop of wire consists of a magnetic moment. That magnetic moment then in an external magnetic field, what that wants to do is it wants to rotate itself so that it becomes aligned with the magnetic field. When this thing is in an external magnetic field, it then wants to align itself because the energy, so the potential energy of that magnetic moment inside of the field is then given by minus the magnetic moment times the magnetic field times cosine of the angle between the two. So that means when I put that loop into the external magnetic field, it wants to rotate itself to align itself with the external magnetic field, since that's the location it has the least amount of energy. If it's anti-parallel to it, that's where it has the greatest amount of energy. And if it's perpendicular to it, it's in between. It actually has zero energy. Now, this is exactly the same thing as the electric dipole moment. So remember that for the electric dipole moment, we had P vector, which is equal to what? The charge times the distance d, where this was negative q, and this was positive q. And d was the vector that pointed from negative q to positive q. And if we put that guy into an external magnetic field, what we found was that the torque was equal to the moment crossed by the external electric field, or the magnitude of the torque then was equal to the moment times the electric field times that angle between the two. And then the potential energy was equal to minus the moment times the electric field times cosine of the angle. So these have exactly the same structure. So here we're just replacing the dipole, electric dipole with the magnetic dipole, replacing the electric field with the magnetic field, but otherwise they have exactly the same structure. So again, torque is going to be mu times B times sine of the angle between the two. So they have exactly the same structure. So I talked about an MRI. This is actually what an MRI actually is. So you take magnetic dipole moments, which are inside of your body, and then you put it into an external magnetic field. What that does is it aligns then those moments then with the magnetic field, which causes that to have a change in energy. And then what the MRI does is it takes those changes of energy for those moments and then pardon me, basically takes that energy and then builds an image from there. Right? So let's do an example. So our example says that we have determined the magnetic dipole moment of an electron orbiting a proton of a hydrogen atom at a given instant, assuming that it's in its ground state with a circular radius of 0.529 times 10 to the minus 10 meters. Okay. So basically what it wants us to do is pretend that we have Bohr's planetary model of the hydrogen atom and then find what is the magnetic moment of this thing. So this is, again, goes back to that MRI. So let's say here's the proton. Here is our electron. And it wants us to assume this thing is orbiting around this guy with a circular radius. So this is our radius in the ground states, which is 0.529 times 10 to the minus 10 meters. So what the electron is going to do is it's going to be moving with a velocity. So this is undergoing uniform circular motion. So we're going to have a velocity vector pointing in this direction. So this thing is going to be a charge which sweeps out a circle in a given amount of time, which is the period, which is then going to create a current. Right? Because remember, current is simply a charge moving. Right? So the first thing we need to do then is determine what is the current. Right? So what's the current? Well, we know the current is going to be the change in charge divided by the change in time. But here, my change in charge is simply the charge of the electron, so that's E, divided by the change in time, which is that of the period. Good. Now, what else do we know? We know the period is related to the velocity. So remember that 2 pi times the radius is equal to the velocity times the time, which means that the period then is going to be equal to 2 pi times the radius divided by the velocity. Okay, so this is the period. So let's plug that in here. So this is going to be the same thing then as the charge times the velocity divided by 2 pi times the radius. We know the radius. Now we need to determine what is the velocity. So we're going to use the fact that this thing is actually undergoing uniform circular motion to then determine what the velocity is. So here we're going to say that the sum of the forces acting on our charged particle is equal to mv squared over r, since this thing is moving in a circle. Now, the next question is, what type of force is holding the electron in orbit around the proton? Is it gravitational force? Is it magnetic force? Or is it electric force? So what type of force is causing our electron here to move in uniform circular motion? So what do you think? Is it gravitational, magnetic, or electric? Those are our 3 options. So who wants to be brave?
Magnetic.
Almost. Not quite. No, it's not magnetic. Even though we're doing magnetic, but it's not magnetic force. Good try.
Electric.
It's electric. Very good. So it's actually the fact that the proton has a positive charge, the electron has a negative charge, which is causing that force between the two, causing it to actually move in a circle. So it's actually the force which is on this is the electric force. Good. So we know the electric force is the same thing as that constant K times then the charge of the first, which is E, times the charge of the second, which is E, so it becomes K E squared, divided by the distance R squared. Right, so this is our electric force. So remember, electric force is the Coulomb force, which is K times Q1 times Q2 divided by the distance R squared. Here we know Q1 is that of the proton, which is E. Q2 is also that of the proton, which is E. Those two have the same force. Good. This R is the same as this R, so let's go ahead and cancel those. So finally what I have is KE squared divided by R is equal to M times V squared. Or if we solve for V squared, we get V squared then is equal to KE squared over MR. Or finally, take a square root. We get V then is equal to KE squared over MR quantity square rooted. Still good. So let's plug that back into our current. So finally, we have the current then is equal to, again, E times V divided by 2 pi R, which is going to be E divided by 2 pi R times the velocity, which is the square root of KE squared. I hate it when you save and do that. There we go. So that's, where was I? KE squared divided by M times R. So this is the current. So now we know the magnetic moment then is equal to the current times the area, but what's the area of a circle? So what's the area of a circle? Pi r squared. Good, that's right. So this is finally going to become the current times pi r squared, which means this is going to become equal to E divided by 2, because this pi here is going to cancel this pi. This r is going to cancel one of this. And then I'm going to be left with 1 r on top, and then the square root of KE squared over MR. So plug in our numbers. We find in this case then that this works out to be 9.27 times 10 to the minus 24. It's going to be 9.27 times 10 to the minus 24 amps meters squared. So this is then the magnetic moment of an electron in a hydrogen atom. Now, what's the direction of that magnetic moment? Even though it doesn't ask us that question, but we can do that anyways. Remember, what we do is we curl our fingers in the direction of the current. So in this case, since the electron is moving this way, it means the current is going like this. Point our thumb in the direction of the magnetic moment, which means in this case our magnetic moment would be pointing in this direction. Everyone's okay? Yes. Good. So that brings us to our second conceptual question, or not conceptual question, sorry, group assignment of the day. So this says we have a 10-turn loop, and I'll talk about that in just a second, of wire lies in a horizontal plane. So basically here, there are 10 loops of wire all stacked on top of each other, parallel to a horizontal magnetic field. So this is my magnetic field pointing in this direction, which carries a current of 2 amps. So basically you have current, say, going in some direction. So it's either going to be this direction or this direction. You're not told, but you're going to figure that out in a second. Then it says that the loop is free to rotate about non-magnetic axles through the center. So that's what these black lines are. So basically, so imagine that here is your loop of wire. Okay, that's being held at this location and this location, which is allowed to rotate this way and this way. Okay, you have a magnetic field, which is, say, pointing at you. And this thing has also a mass at this location, which is a 50-gram mass, hangs on one edge of the loop. So it wants to know, what is the strength of the magnetic field to keep this thing from rotating? So basically what's going to happen is, here's my loop. I'm going to put a mass on it over here, which means it's going to feel a torque, so it wants to rotate in this direction. However, what we want to do is run a current through here so that it ends up creating a torque. So as this thing rotates this way, it wants to create a torque going back in this direction. So you want the magnetic torque going this way, the gravitational torque going this way, so that the net torque acting on the system is simply equal to 0. Okay? So basically all that means is that you want the magnetic torque equal to the gravitational torque. That's basically it. Okay? So then it wants to know, for the magnetic torque to equal that of the gravitational torque, what must be the size of the magnetic field to make sure that that happens? Now, let's talk about what this 10 loops mean. Now, even though I wrote down before that mu was equal to I times A, the most general way to write mu, so actually mu is equal to N times I times A, where N here is equal to the number of loops. So we wrote down before where mu was equal to I times A. This is the magnetic moment for one loop. But if you have more than one loops, each one carries the same amount of magnetic moment, which means that we usually write it in general this way, which is N, which is the number of loops times then the current times then the area. So again, here what you're looking at is, here's the side. So again, you have a gravitational torque pulling in this direction. So you got mg pulling this way. And basically what we want is we want the magnetic torque to then be pulling it in this direction. So this is going to be mu times b. And we want to set those two things equal to each other. So we want simply mu times b then is equal to mg. From here, you just want to solve for b. So that means b then is going to be equal to mg divided by mu. So you're just looking for the size of that magnetic field. And again, here mu is going to be equal to 10 times the current times then the area. Okay. It's okay. For the gravitational torque, oh, sorry, we're missing R here. There we go. We need an R. That was only the force, so we need an R there. So in this case, R is going to be, going back to our picture, half of the 5 centimeters. Right, because R points from the center to the location of the force, which in this case is 2.5 centimeters. So here R is going to be equal to 2.5 centimeters. Okay. It's okay? I did about 90% of the work for you. So now he's going to do the rest of it. So that should be good. All right, so let's do our breakout rooms again. Looks like we lost some people. All right, so let's do, I want to add a room. I want to delete that. Okay. All right, I'm gonna increase the size of the rooms. There we go. Okay, open the rooms. Unassigned. Okay. So, Julie, I'm going to assign you two. Two. Okay. Miranda, we'll assign you two. And Emma, still here. Two. Okay. Two here. Mm-hmm. Come on. All right, how are we doing, ladies?
Think we're doing good.
Think you're doing okay? Good. 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 All right, how are we doing, ladies?
Just
Doing-
plugging and chugging.
Nice.
Same.
I heard
And
thunder.
the area is just 0.1 times 0.05 meters.
That's my house. The rain here is really loud right now.
Is it? Okay. Yeah, that's right. So it's 10 centimeters times 5 centimeters. So yeah, 0.1 times 0.05. That's right. Yeah, we had a lot of thunder and lightning around, what, maybe 2 this morning? I don't remember exactly what it was, but then again around 4. So
Like I was telling them, I woke up at 6 a.m. to go for a training run and it was already raining and I was like, nope, going back to bed.
yeah, I was supposed to get up. I got up
About
at
later there was some lightning and I was like, I'm glad I'm not out there.
yeah, I got up at 4 to do early morning prayers, and then I usually do my workout and then go for a morning skate. But it was raining so hard, I was like, I can't skate in the rain. That's just not gonna work. Rollerblading on water just doesn't work very well. Right.
Okay.
Hello again. Everybody still doing okay? all so quiet.
I think we're all muted.
It's hard to talk to each other when you're muted. That's fine.
So I just
Yeah,
that the system already knew that the answer was going to be in millimeters.
that's how I thought of it as. And so I was just like trying different number. And I was like, wow.
I'll change it. Don't worry. It'll be fine.
I know. I used up my first attempt on the wrong part of the problem. And then I was like talking to some of the girls in the group text, and they were like, I keep putting in these answers and it keeps telling me it's wrong. And I was like, well, my math looks the same as your math, so maybe I should ask before I waste my second attempt.
Yeah.
Typically it works better that way. Yeah.
Yeah.
Okay, I got 0.122.
That's right.
The answer was 0.12. So yeah, that's it. Good. All right. All right. Everybody get the answer? Good. All right. So we'll disband the rooms and start talking about the next stuff. All right. Welcome back, everyone. So our next topic we're going to talk about is, so we've seen how to determine the direction of the magnetic field for a straight wire, but now let's actually talk about the magnetic field of that straight wire. So what's the structure of it? What should it actually look like? So to do that, let's talk about what we learned in lab. So in lab, what we learned was that so from the video, what they did is they took that straight wire and then they put a compass above it, and then they were measuring the magnetic field at different distances. And then in the lab, you're supposed to plot the natural log of the magnetic field versus the natural log of the position, because we were using that the natural log of the magnetic field was then equal to natural log of K, whatever K is. That's just some constant, so we didn't really care that much. Plus n, where n is the power times the natural log of K. So remember that we're writing here that B was equal to some K times R raised to the nth power. So when you plotted that, what you should have found was that this line, the best fit line, had a slope of -1. So basically, from this, what we should have learned then was that B was equal to K times R to the -1 power, which is the same thing then as K divided by R. So what this means is that if we have a wire which is carrying current, so again, right-hand rule number 1 says we put our thumb in the direction of the current, our fingers curl around in the direction of the magnetic field. So this is our magnetic field B. What this also then tells me then is that if I am at the center of the wire and I go to some distance R away, then the magnetic field then falls off as 1 over R. So if I actually did some more experiments with this, what I would finally find then is that the magnetic field of a straight wire is given by μ0 times the current, where inside of here K is the current, divided by 2 pi times R, where μ0, which is equal to 4 times pi times 10 to the -7th, and that has units of, so this is meters times Teslas divided by an amp. So this is mu. Mu is what's known as the permeability of free space. This is the magnetic version of epsilon naught. So basically this has kind of the same meaning as epsilon naught. So again, it's basically, to describe it, it's kind of how readily, easily is it for a magnetic field to fill all of space. Okay. So this is the magnetic field then of a straight wire. So for a straight wire, this is μ0 times the current divided by 2 pi times R. where R, again, is going to be the distance from the center of the wire to whatever location it is that we're looking at. So it's going to be our location, say point P. Point P, there we go. So, having said that, we can now go back to the force on a straight wire and then look at what happens if I have two straight wires. So meaning that, I never put out the garbage this morning. Whoops. Okay. Hopefully I don't miss it. I'll have to do that between class and lab. Yeah?
I'm gonna take my bath, but I can't take a bath while putting this in the water, and besides, this towel is too big, and also I can't hang it on the closet to the door.
Well, just put it on the door handle. Put it on the doorknob. You'll be fine. Okay. I'll give you a hand in a minute. Okay. Sorry. Okay. So, anyway, so let's say that again. So now we have two wires which are next to each other. So let's say this top one has current I2, this bottom one has current I1, and let's say these two are separated from center to center distance of a distance of D. We want to know what is the force on one wire by the second wire. So we know that, let's say the force on wire 1 here is going to be equal to then what? The current through wire 1 times the length of wire 1 times then the magnetic field generated by wire 2 times sine of the angle between the two. Okay? Where in this case, this is going to be the angle between the magnetic field and the angle between L. Okay? So this has a length of L2, this has a length of L1. And for concreteness, let's say that current I1 is running in this direction. So I1 is going this way. Okay. Simultaneously, we also know that the force on wire 2 is then going to be equal to the current going through 2 times the length of 2 times magnetic field from wire 1, because what's happening is this one is feeling the magnetic field from him, which is generating force. But simultaneously, this one is feeling the magnetic field from him, which is also generating his force, times then sine of the angle between the two. Good. So we want to know then, let's look at wire 2 here and determine what type of force is he going to feel, okay, by looking at wire 1. So first off, we know from wire 1, we know our thumb is going to point in the direction of current 1. Our fingers will curl around in the direction of the magnetic field, which means our magnetic field B1 is going to do something like this. And this is B1. Now, since it is circular, what we care about is the projection of it onto the page, which means by the time it is at wire 2, it's going to be pointing into the page. So anywhere up here, magnetic field 1 will be pointing then into the page. Now, since the current has to move through the wire, either going in this direction or in this direction, that means that what? The current will be going either to the left or to the right. Magnetic field is into the page, which means that this angle here is actually equal to 90 degrees. So this is going to be 90 degrees. Which means that F2, the force on wire 2, is going to be the current I2 times L2 times simply B1. Now, what we also know is that B1 is from this current, so this is going to be mu naught times current I1 divided by 2 pi times the distance between the two, which is simply D. So that means the force on 2 by 1 is going to be equal to mu naught I1 times I2 times L2 divided by 2 pi D. The force on wire 1 is going to be by the same thing, mu naught I1 times I2 times L1 divided by 2 pi D. So these two forces will be exactly the same in magnitude. Let's now talk about the directions. So let's look at two different scenarios. So let's look at scenario number 1. We're going to take current I1 going in the same direction as I2. So I'm going to write I2 going in the same direction as I1. So what our right-hand rule says is that we're going to point our fingers in the direction of current I2, which is going to be in this direction. We would curl them towards the magnetic field. So we have to put our palm in the direction of the paper, curl down towards the magnetic field B1, which means that this guy is going to feel a downward force in this direction. So this is going to be F2. Now, since current is running in that direction, we put our thumb in the direction of I2. Our fingers curl around in that direction of the magnetic field, which means, again, our magnetic field is going to go around this way. So this is going to be B2, which means down at wire 1, we care about the projection, so it's going to be coming out of the page. So B2 is going to be coming out this way. So for him, we'd again point our fingers in the direction of the current. Magnetic field is now pointing outwards, so we have to rotate the back of our hand in this direction, curl our fingers in the direction of the magnetic field, which means now the force is going to point towards the second one. So now F1 is going to point in this direction. So what this tells us is that what? When the currents are in the same direction, this then equals an attractive force. So whenever I have current running through wires, those two are in the same direction, those two wires will feel an attractive force between them. They will be attracted towards each other. Okay. Now, what happens if we now change the direction? So again, let me redraw real quick. So let's put this guy this way, this guy here. Again, let's take I1 is going in this direction. So this is I1, which means again, B2 is going to be, I'm sorry, B1 is going to be into the page up here. So this is B1. Now let's take the opposite case. Let's take I2 going in this direction. So if I2 is going in this direction, what this means then is what? So now I put my thumb in this direction, my current would rotate now in this direction, which means our magnetic field now goes this way. So this is now B2, which means B2 is now into the page anywhere along wire 1. So this is now B2. So in this case, again, we point our fingers in the direction of I1. I1 is this way. Magnetic field is now into the page. So our thumb would now point downward. That's a whole bunch of thunder. Would now point in this direction. So F1 is now going to point downward instead of upward. Simultaneously, onto wire 1, or sorry, wire 2, current is now going in this direction. Magnetic field is into the page, so I put my fingers inward. My thumb would now point upward, which means the force on wire 2 now is upward. So from this, what we learn now is what? Whenever I have currents in the opposite directions, this now results itself in a repulsive force. So whenever I have two parallel wires, each one carrying current, the force on each one of those two wires are equal and opposite by Newton's third law. How these guys are opposite to each other is going to depend now on the direction of the currents. So if my currents are in the same direction, that means I now have an attractive force, where if they are in opposite directions, it now results itself in a repulsive force. But again, magnitudes are the same, and the magnitude for each one is simply going to be the force is equal to mu naught times current 1 times current 2 times the length divided by 2 pi d, where again, d is the center-to-center distance between the two. So as long as I have two parallel wires, the force will be exactly this amount. So let's now do a quick example. And then we'll save the other example for tomorrow since we're kind of running out of time. That one. Good. So this one says that we have a horizontal wire carries a current of 80 amps, and that's going to be I1. A second parallel wire, which is 20 centimeters below the first one, carries a current I2. And it carries I2 such that it will be levitated. So it will not fall under its own gravitational weight, where the mass per unit length of that lower wire is 0.12 grams per unit length. Okay. So here what it wants to know then again is what is the current I2 to keep this thing from falling? So let's draw a picture. So what I have here is current 1 in wire 1. So just for funsies, let's say current is going in this direction. So this is I1. And we know I1 is equal to 80 amps. Some distance below this guy, here is wire 2. So this is wire 2, which is a distance D, where D was equal to 20 centimeters below wire 1. This thing also has a mass, which means it's going to feel a gravitational weight. So we know it has an mg downward, where we're told that the mass per unit length, which is what we called mu before, which is linear mass density, is equal to 0.2. Where am I looking? 0.12 grams per meter. Okay. So from here, it wants to know what is the current in wire 2. Okay. To keep this thing from falling. So this thing is simply going to levitate, which means the net force acting on this guy has to be equal to 0. So what that means then is if we draw, here's our wire. This is wire 2. We know we have mg acting downward. We have a gravitational force downward. So we have to have a magnetic force upward. And we want to know what is the current I2 to keep this thing such that it is levitated. So the sum of the forces are equal to 0. So let's choose positive y to be upward. So the sum of the forces in the y direction are equal to 0. So first question, even though it's not asked in the question, but what direction then is current I2? Is I2 going in the same direction as I1, or is it going in the opposite direction? So what type of force do I need? So I need a repulsive force or an attractive force?
It would be the same direction because
Good.
we need an attractive force.
Exactly. So we want an attractive force to keep it from falling. So in this case, we have to have it in exactly the same direction. Very good. So good. So here we know that's what? We need our magnetic force minus mg then is equal to 0, which means our magnetic force then is going to be equal to simply mg. We know our magnetic force then is going to be mu naught times current I1 times current I2 times the length of the wire. Pardon me, divided by 2 pi times d, where d again is the distance between the two, and that's equal to mg. We know I1, we know mu, we know d, we don't know L, but notice when I divide L on the other side, that's going to give me m over L, and we do know m over L is equal to 0.12 grams per meter. Okay. So we're going to know that. So let's solve for I2. So finally this tells me I2 then is going to be equal to what? So let's divide L over here, so it's going to be m over L. Okay. Times then 2 pi times g times d divided by mu naught times I1. Okay. Where again, m over L, we know that's simply given by here. We know 2 pi g, we know d, we know mu naught, we know I. So from here we can plug in all our numbers, and what we find in this case is that I works out to be about 15 amps. So this is our results. Much time we got? 5 minutes. Is it okay?
Can you explain again why you chose I2 to be in the same direction?
Oh, because what we had learned on the other page was that if they're in the same direction, that makes itself an attractive force. Or if they're in opposite directions, it has to be a repulsive force. So what we want here is that since the gravitational force is pulling downward, and we know we want the net force acting on the wire to be 0 because it's levitated, we're keeping it from falling down, then that has to manifest itself as an attractive force, because if it was a repulsive force, both of the two forces would be in the same direction, so this thing would just accelerate downward. So it would be pushed away from it. So since we want something to counteract that gravitational force, we need it to be pulling upward. So what we need then is that this one is feeling a force upward, and this one is going to feel a force downward. So that these have to be, pardon me, has to be attracted then to the top wire to keep it from falling. So since it's an attractive force, that tells us by what we learned on the previous page that these two currents then must be in exactly the same direction. Does that make sense, Kelly?
A little bit more.
A little bit more, okay. Good. So again, if they were in opposite directions, what happened then is that this would result itself in a repulsive. So each one would feel a force in these directions if it was pointing this way, which means that now I would have two forces pushing down with nothing keeping it upward. So in that case, the sum of my forces then would be equal to MA, because now I would have the magnetic force plus the gravitational force would be equal to MA. So there'd be nothing here which is in the opposite direction to keep it from falling. So it would only be accelerated, and it would actually be accelerating now at a rate faster than G. So it wouldn't be a free fall, but I would be pushing it down and accelerating it down faster. Okay. So in that case, it would have an acceleration greater than G in this case. But here, specifically in the problem, since we want it to be not falling, so if we go back to the problem, here we go. So it says, so it does not fall due to gravity. So that means we have to have the magnetic force pulling upward to make sure that this guy is not falling downward. So we need two forces in opposite directions. Does that make sense? Now that would be different if we were looking at the opposite. So if I was looking at the top wire here, and if I was looking at that one, then I would have gravitational force downward. In that case, I would need a repulsive force to keep that one from falling. So it just depends on which wire that I'm actually looking at. But in this case, since I'm looking at the bottom wire, I need it to be pulled upward. Where if I was looking at the top wire, if I wanted that one to not fall, then I would need a repulsive force because it would have to counteract the gravitational force. So in this case, I'm always just looking at what's going to counteract that gravitational force, depending on which wire that I'm looking at. So if I'm looking at the bottom one, what's going to counteract gravity would be an attractive force. If I'm looking at the top one, what's going to counteract gravity would be a repulsive force. So it just depends on which wire I'm being specifically asked about. That makes sense? And it is pouring. Good time for me to bring out the garbage. Okay. So, everybody doing okay? Not too bad? Okay, so we have one more example, but we're not gonna have time to do that, so we'll do that tomorrow. So tomorrow, what we'll do is we'll do one more example of this. Something that involves more than 2 wires. So we're gonna look at something that involves 4 wires. And then we'll do another group exercise, and then we'll talk about solenoids. So a solenoid is actually the magnetic equivalent of a parallel plate capacitor. So remember a parallel plate capacitor is actually a capacitor where that capacitor's point is to put it into a circuit to store energy for later use. A solenoid is the magnetic equivalent of that, which means that its purpose is to be put into a circuit to store energy for later use. So we're going to start looking at those tomorrow, and then that'll finish off this chapter, and then from there we'll start the next chapter. So we'll start the next chapter, chapter 21 tomorrow, and then that'll be the end of everything for the exam. So that'll take us a couple of days to go through, and then we should be done either Wednesday or at least partway into Thursday for Friday's exam. So everyone's doing okay? Not too bad. Good. So I'll see everybody in lab then in a little bit. So this will be our last lab. Very exciting. And again, don't worry about the points for the lab. I'll give you all that stuff back. Don't you worry too much about it. So I'll see everybody in a little bit. I'm going to go outside and get wet so I can bring out the garbage. All right.